Good afternoon, everybody. On behalf of the Brazilian Logic Society and the Logic Interest Group of the Brazilian Computer Society, it's a pleasure to have another seminar, Logicians in Quarantine, which is part of the Logic Supergroup. And it's a great pleasure for me to introduce Professor Gilles Dowek, which kindly accepted our invitation to give this talk. And we present Logipedia, a system-independent encyclopedia of formal proofs. Gilles, thank you very much.
Okay, thank you very much, Bruno, for your invitation. I wish I could be with you in Niterói or in Rio, but obviously we have to do with the situation. Today I'm going to speak about an equivalent of Wikipedia, but which is much smaller, of course, because it only contains formal proofs. But the idea is to share formal proofs exactly as Wikipedia allows us to share knowledge in general. And before we speak of Wikipedia, let me remind you how you wrote your first program maybe 70 years ago. And in the early ages, when you wrote a piece of software, for instance, a text processing system, you had to choose a representation for your data. And by doing so, you involuntarily defined a format. So for instance, you had to decide that your text was a sequence of symbols, and for each symbol you had to choose a number. So maybe you chose a number 97 for A, or maybe 1, or maybe 0, or maybe 98. But you had to make a decision. And by doing so, you defined a format which was very specific to your piece of software. Of course, now we are not proceeding this way anymore. So first, a group of people define a format, such as the ASCII format, where A is indeed 97. Or you have formats for data exchange, like TCP/IP or HTTP, or you have formats for structuring text, such as HTML, Unicode, and so on. And when you write a software, you have to comply to a format. It doesn't mean anything to develop, say, a web browser that would use a language that would be a slight variation of HTML, but instead of using this keyword, you would use another one, because nobody would use your browser. So now we first define the format of the data. We define standards. And then when we develop a piece of software, we have to comply with the standard. In fact, this is how computer science and computer development, software development works in general. But there is just one exception, and this exception is us. So we have many ways to represent proofs in different systems. And this is why when Georges Gontier, for instance, developed his proof of the four-color theorem, we didn't say that he had developed a formal proof of the four-color theorem, but that he had developed a code proof of the four-color theorem, which means a proof expressed in the very specific language of Coq. And we can say the same thing for Hale's theorem. Hales developed himself a formal proof of his theorem, and he did that in HOL Light, so we have a HOL Light proof of Hale's theorem. Of course, we all believe that we could express Hale's theorem in Coq or the four-color theorem in HOL Light, but currently we don't have a HOL Light proof of the four-color theorem. So this creates a number of problems. One of them is interoperability. So if someone has developed a lemma in some system, then someone else cannot use this lemma in a different system. But there is also a problem of sustainability. For instance, there is a huge library which has been developed in the language of the Mizar system. And we are not completely sure the Mizar system will still exist in 50 years. And we have to do something with this library so that it's not lost, even if the development of Mizar stops in a few decades. We have already lost, in fact, all the LCF developments, and for the automat development, they were almost lost, but they were saved from loss. So why does it seem to be more difficult with formal proofs? Probably the reason why we don't have such a standard for formal proofs is just that we are less mature than other communities, such as text processing systems. But maybe it's a little bit more difficult to define a standard for formal proofs than for text processing. And one reason is that the proofs we develop, they are expressed in different theories. For instance, it would mean nothing to have a prover or interactive proof system to develop proof in Euclidean geometry and to expect to use this theorem in another system that would be specialized in hyperbolic geometry. So the theories are different, and this is why we cannot move proofs from one system to another. In the same way, if we have an implementation of set theory without the axiom of choice, and we have another implementation of set theory with the axiom of choice, then we cannot prove the same theorems, we cannot develop the same proofs in the two systems, so there is no way we can choose a standard for proofs, and we would be able to move proofs in one direction and in the other. But of course, there are a few things we can do. For instance, if we have a proof in set theory without the axiom of choice, then we can translate it to the language of set theory with the axiom of choice. In fact, the translation is just the identity, just an embedding. We have nothing to do because the proof in set theory without the axiom of choice is per se a proof of set theory with the axiom of choice. And in the other direction, it does not always work. But if we have a proof in ZFC that happen not to use the axiom of choice, of course, it is a proof in ZF, and we can express it in ZF, that is set theory without the axiom of choice. Sometimes we can do a little bit better, and we can transform the proof before we move it from one system to another. And this is my favorite example of a theorem. So the theorem proves that there exists a basis in the vector space R square. And the first proof you can imagine is to use the incomplete basis theorem. So the incomplete basis theorem tells you that every vector space has a base. And of course, this theorem, the proof of this theorem has to use the axiom of choice, because we know that this theorem does not hold in models of set theory where the axiom of choice is not valid. But there is a much simpler proof in this case. It is to provide actual basis, and the basis is made with the two vectors 1, 0 and 0, 1. And to prove that 1, 0, 0, 1 is a basis of R square, you don't need the axiom of choice. So it's a good test to know if your colleagues are mathematicians or logicians, is to ask them which of these proofs is the more general. So many mathematicians think the first one is more general because it applies to all vector spaces and not just to R square. But of course, the second one is much more general because it holds in any model of set theory and not only in models of set theory with the axiom of choice. So it gives us much more information about the models of set theory. And this transformation, transforming the first proof into the second one, it can be done by hand. In this case, just because I know algebra very well, that I knew that this system, that this vector space had a basis, and I was able to provide one. But in many cases, we can also have systematic algorithms that at least attempt to transform proofs. From time to time, they fail. And a very good example of this is constructivization algorithms. We have a proof in classical logic, and we have an algorithm attempting to transform this proof into a constructive one. It doesn't always work, of course, because some theorems have a classical proof but no constructive proof, but it works in many cases. And in fact, we see that the idea which is at the basis of reverse mathematics, which is to transform proofs so that they squeeze in smaller theories, is at the basis of interoperability. Because as soon as you transform a proof that uses the axiom of choice into one that doesn't, then you can export your proof from one system to another, even if the target system does not use the axiom of choice. So, of course, what I just presented is not what is usually called reverse mathematics, and there are three differences. The first one is that here we deal with formal proofs, so we are not really interested in transforming pencil and paper proofs. We want really to do that on formal proofs. Then we are not really interested in fragments of arithmetic, which is the core of reverse mathematics, but we are more interested in more expressive theories such as set theory, type theory, and so on. And then we want to, before we possibly transform the proof, the first step of our approach is to analyze the proof and to try to understand which axiom it uses, so that maybe we can transform it in such a way that it uses less axiom. So how is it possible that we design such an algorithm to transform proof of ZF in ZFC? As I said, this is trivial, and some proofs that we find in ZFC back in ZF. And one of the reasons why this is possible is because set theory and set theory with the axiom of choice are expressed in the same logical framework. And this logical framework is called predicate logic. So we see that we just said that it's not possible to have a standard for proofs because the proofs are expressed in different theories. But predicate logic as a logical framework is a standard not for proofs, but for languages in which we define these theories. And moreover, predicate logic is a logical framework where each theory is expressed with a number of axioms. In the case of set theory, we have maybe 7 or 8 axioms, including axiom schemes, of course. And this permits to raise the question, when you have a proof pi, you can ask yourself, which are the axioms that are used in this proof pi? And if, let's say, among the 8 axioms of set theory, only 7 are used, let's say all the axioms except the axiom of choice, then you know that the proof can also be expressed in a different theory, which is a set theory without the axiom of choice. So the invention of predicate logic was really a revolution in logic. Because before we had this first logical framework, every logical system was defined independently of the others. So since Euclid, geometry, arithmetic, think of piano arithmetic, set theory, think of Cantor set theory, or even Zermelos set theory. So each of these systems had its own syntax, its own notion of proof, and nothing was shared between geometry and arithmetic. And when, after 50 years of research, because let's say that the first attempt of predicate logic was a Begriffsschrift that was 50 years before 1928, after 50 years of effort, Hilbert and Ackermann came with this logical framework. It was really a lingua franca in which many theories could be expressed. And the 3 major theories of that time, of the 20s, so geometry, Euclid geometry, Hilbert geometry, arithmetic, and set theory, could be expressed in this same logical framework. It means that the conjunction that you have in geometry, the conjunction that you have in arithmetic, the conjunction that you have in set theory are just one symbol. And the deduction rules that you have in geometry, the deduction rule that you have in arithmetic are the same because they belong to the framework and not to the theory. And to define a theory, you just need to provide a set of symbols and a set of axioms, and only the language and the axioms differ from one theory to the next. But in fact, this revolution, as many revolutions, unfortunately fell short. Because at that time, there was another theory, which was the first version of type theory presented in the Principia Mathematica. And this theory was at that time very popular, probably even more popular than set theory or geometry or arithmetic. But Hilbert and Ackermann did not give any expression of this theory in predicate logic. And soon after, other formulation of type theory, for instance, Church's formulation of type theory, which is based on lambda calculus, were impossible to express in predicate logic. So why are they impossible to express in predicate logic? because in the language of Church's type theory, you have a symbol, the lambda abstraction, that binds a variable, and there is no way in predicate logic to define a function symbol that binds a variable. And then in 1970, Martin Löf proposed a new type theory, and then in 1985, Cocan and Huet proposed the calculus of construction, and then Shankar proposed type theory with predicate subtyping. And all these theories were not presented as theories in predicate logic, but as theories that were independent of each other and independent of predicate logic. So this led the logicians to have three possible attitudes towards logical frameworks. So some of them consider that the notion of a logical framework was dead, so we didn't need any logical frameworks, and we could not use any logical framework. And this is basically the culture in which I was raised. Some others tried to express Russell's type theory or Church's type theory or the calculus of constructions in predicate logic, and these theories had to fit in predicate logic by will or by force. And we can say that Martin Davis did this work for a variant of Church's type theory. But in my opinion, Henkin, before Davis, was not too far from it. There are at least two papers of Henkin where he never formulates the project of expressing a type theory within predicate logic. But if you read between the lines, you can see that he's going in this direction. And I tried to do this myself at the end of the 20th century with the calculus of constructions. And in fact, I can say I succeeded because eventually I got a set of axioms for the calculus of constructions in predicate logic. But these axioms were so numerous and so complex that I was not even able to prove a single lemma about this system. So it was a success, but probably also a failure. So at this point, I thought that predicate logic probably was not the best logical framework to express something like Martin Löf type theory or the calculus of constructions. And I understood that there was a third line of research that wanted to transform predicate logic to extend it to a better logical framework. And what's wrong with predicate logic? So we can see that there are probably 5 limitations of predicate logic. So the first one, I have already mentioned it. It is that we cannot express a term such as lambda xx in predicate logic because lambda binds a variable and function symbols in predicate logic do not. Then we see that we don't have a syntax for proofs in predicate logic. We have a syntax for terms. We have a syntax for propositions. But then when we want to write proofs, we have to use something which is slightly on the side of predicate logic, such as natural deduction or sequence calculus or a Hilbert system. We have also no good notion of computation. So for instance, if you want to prove that 2 plus 2 is equal to 4, then you have to provide a proof as if you were proving Fermat's last theorem. So you have to use the axioms of arithmetic to prove your statement that 2 plus 2 is equal to 4. And you cannot just say, well, I know an algorithm for addition and I can add 2 plus 2 and I will get 4. There is also no good notion of proof reduction. So of course, if you do not consider any axiom, we have Gensen's cut elimination theorem. So we have a notion of proof reduction in this case. We have a notion of proof reduction for arithmetic. Then we had a notion of proof reduction for simple type theory. But we don't have a uniform notion of proof reduction. Each time we have a new theory, we have to define what it means to have a notion of proof reduction for this theory. And finally, predicate logic is classical and they are not constructive. So of course you can design a variant of predicate logic, which is constructive predicate logic, but then it's a different systems, and you don't have the choice to do a classical proof or a constructive proof. It's decided by the framework itself. So this led logicians to define new predicate logics, and here are a few examples. So the first problem, the problem of bound variables, was solved first in lambda prolog and in Isabelle. Then the lambda pi calculus, the so-called Edinburgh logical framework, added proof terms to lambda prolog or Isabelle. So we had there logical framework where we could express theories with bound variables, and we had an explicit syntax for proofs. Then with deduction modulo theory, we tried to add to predicate logic a good notion of computation and a good notion of proof reduction. And independently, ecumenical logic was developed in order to address this issue of classical versus constructive proofs. And in fact, in this talk, I will speak a lot about ecumenical logic because I decided that it would be my tribute to the Rio community when ecumenical logic was almost born in Rio. So I thought it was a good opportunity to talk about it. So we see that we have lambda prolog, Isabelle, the lambda pi calculus, deduction modulo theory, pure type systems, ecumenical logic, and the lambda pi calculus modulo theory that came later generalizes all these logical frameworks. And the system I'm going to speak about before I speak about Logipedia is called Deducti, and Deducti is an implementation of the lambda pi calculus modulo theory. So Deducti is itself an implementation of a logical framework where we can have bound variable, we have a syntax for proofs, we have a notion of computation, we have a notion of proof reduction, and we can mix classical and constructive proofs. So let me show you a detailed example. And let us build together minimal constructive and then ecumenical predicate logic in Deducti. So first, you have to understand that Deducti is a much weaker framework than predicate logic. So it's one reason why it is more general, because it is much weaker. So there is no primitive notion of term, there is no primitive notion of proposition, there is no primitive notion of proofs. But there are tools to build these notions. And in fact, as its name expresses, the lambda pi calculus modulo theory is just an extension of the lambda pi calculus. So the lambda pi calculus is a type lambda calculus with dependent types. And the modulo theory part expresses that in the lambda pi calculus modulo theory, we can also use computation rules instead of axioms. And I'm not going to present Deducti in details, so you can think, if you like, that Deducti is just simply type lambda calculus. But each time I will use a feature of Deducti, I will mention it so that step by step, you will see what Deducti is, but what is more important is you will see what you can do within Deducti, which is much more important. So first, I said we don't have a primitive notion of term. So of course, we have the lambda terms of the framework, but what I mean here is that we have no equivalent of the object terms, for instance, that in arithmetic express natural numbers. So if we want to do that in Deducti, we have to define a primitive type. And in Deducti, a primitive type is just a type variable. So we have to declare a type variable, which is called I here. So to do so, we just declare a variable I of type. And the keyword type here is one of the 2 or 3 keywords of Deducti that we are going to use. And then we can define, let's say, function symbols, but function symbols are just symbols of type I, arrow I, arrow I, arrow I, arrow I. And here I have two of them. 0 has type I, and successor has type I, arrow I. And this arrow that you see in the type of the successor, it's another primitive symbol of deductive. Deductive, like any like any type lambda calculus, has a primitive notion of arrow types. So this is it for terms. So the term, you can apply the symbol successor to 0, and then you get another lambda term of type I, and this lambda term of type I is a term that expresses a natural number. Now that we have rebuilt the notion of term, let's do the same thing for the notion of proposition. And to do so, we have to define another deductive type, which is called prop here. And if we want to have predicate symbols, like the even symbol, we have to declare them with the type I, arrow, prop. And again, you can apply this predicate symbol even to the number successor of 0, and you get a term of type prop, and this is what we call a proposition or a formula. And as we are in minimal predicate logic for now, we just need to declare two other constants, one for implication, which of course is given the type prop, arrow, prop, so that you can apply this symbol to two propositions to get another proposition. And we need to have a quantifier to quantify our variables of type I. And here you may be surprised by the type of the for all, but it's not very surprising because you remember that the for all quantifier binds a variable. And we use the same trick as we do in Lambda Prolog or in Isabelle or in the Lambda Pi calculus. And in fact, it's a trick that Church already used in his 1940 paper to express quantified propositions. You do not apply the for all quantifier to a variable and a proposition, but you first abstract this variable in the proposition with the lambda, which is primitive in deductive. So we build the term lambda x of type IA, and this term has type I, arrow, prop, and we then apply the quantifier for all to this term. And to be able to do so, the for all quantifier must have a type that takes as an argument a function from I to prop and returns a proposition, hence the type that you can see on the bottom line of this slide. And this technique is sometimes used higher order abstract syntax, but the idea is just that when you have a bound variable, you bind it with the lambda of the logical framework, and then you apply symbol to this function. So we have built now the notion of term and the notion of proposition, and we have to build the notion of proof. And of course, there are many ways to define proofs in deductive, and here I have been using Brouwer-Haitink-Kolmogorov interpretation, but you could maybe just declare your deduction rules if you like. But if you want to use the Brouwer-Haitink-Kolmogorov interpretation, then you know that a proof of A implies B must be expressed by a type term that itself expresses a function mapping the proofs of A to the proofs of B. So what we have to do is to define a type for the proofs of some proposition A. So if we want proof of A to be the type of the proofs of A, then we have to declare this symbol proof, PRF, and this symbol must take as an argument a proposition, and it must return a type, as this type will be the type of the proofs of A. And you see that here we use for the first time one feature of deductive, which is that deductive supports dependent types, because proof is a so-called type family. It is not a type in itself, and it's not a function from, say, propositions to proposition. It is a function from proposition to types. And the possibility to define a function that takes as an argument an object like a proposition and builds a type is what is called dependent types. So we know that proof of A is now the type of the terms that are proofs of a proposition A. And if we follow the motto of Brouwer, Heiting, and Kolmogorov, this term, the identity term on proofs of A, so lambda xx, where x is a variable of type proof of A, it's a function that maps a proof of P to a proof of P. Sorry, I said proof of A, I meant proof of P, of course. So this lambda term that expresses a function that maps proofs of P to proofs of P should be considered as a proof of P implies P. That is, it should be a term of type proof of P implies P. But it's not a term of this type because as any lambda term, it has an arrow type, and this arrow type is the arrow type of the functions mapping proofs of P to proofs of P. So the type is proofs of P, arrow, proofs of P. And you see that you have two arrows here. The double arrow is, which is in blue, is the implication that we have defined in this theory. And the simple arrow, which is in black, is the primitive symbol of deductive. So now we want to identify the proofs of X implies Y and the functional type. So this is the type of the proofs of X implies Y, this type proof of A, X implies Y. And we want to identify this type with the functional type proof of X, arrow, proof of Y. And here we have to use another feature of deductive, which is that deductive allows the declaration not only of constants, not only of variables, but also of rewrite rules, of computation rules. And we are saying that this type, proof of X implies Y, rewrites, computes, transforms to this functional type, proofs of X, arrow, proofs of Y. In this way, we see that the term lambda xx, where X is a variable of type proof of P, then is indeed a proof of P implies P, that is a term of type proof of P, arrow, proof of P. And we do the same thing for the universal quantifier. Again, Brouwer, Heiting, Kolmogorov interpretation tells us that proof of for all P should be a function mapping any element Z in I to a proof of P of Z. And this is what we are expressing here. And you see that the arrow has to be generalized to a dependent product because we had dependent types. So it is possible that we build this function that takes as an argument an object Z and returns a term which has the type proof of P of Z, where Z occurs. So we cannot just write this type I arrow something. We have to use this dependent product. Now we are done with minimal predicate logic, and it's not too difficult to prove that if you have a proposition A, then any term in the type of the proofs of A can be translated to sequence calculus or to a natural deduction proof of A, and vice versa. So we have a sound and complete implementation of minimal predicate logic in deductive. Now let us turn to constructive predicate logic, which is almost the same thing, except that besides implication and the universal quantifier, we also have other logical constants, other connective and quantifiers, truth, falsehood, negation, conjunction, disjunction, and the existential quantifier. So you may remember that in the Principia Mathematica, Russell already defined a conjunction from the universal quantifier and the implication. And the proposition A and B was defined as this proposition for all C. A implies B implies C implies C. And it's not too difficult to see that if you have a proof of A and a proof of B, then you can build a proof of this proposition. And if you have the proof of this proposition, you can build a proof of A and you can build a proof of B. Hence, it behaves exactly like the conjunction of A and B. Yet, to do so, in the Principia Mathematica, in Russell's type theory, you use the fact that you have a quantifier over propositions, because here C is a propositional variable, and you have to quantify over C to be able to build this proposition. And of course, here we are in predicate logic. We are not in type theory. So the for quantifier can quantify only over the elements of I. And we have made everything we could to restrict this quantifier to quantify over elements of I, because we want to formalize predicate logic in deductive and not type theory. We are going to formalize type theory later, but at this point, we want to have predicate logic. And in predicate logic, you can quantify over the elements of the universe of discourse, but not over the propositions. So we are not going to add another quantifier on proposition yet. But you see that even if you cannot quantify over proposition in the theory itself using the for all quantifier, you can do that in the framework. So what does it mean? It means that in deductive itself, you can build the product type pi x in A, B for any A and B of type. And in particular, you can build this type, which is in the middle of the slide. So it's pi z of type proof of x implies arrow proof of y, arrow proof of z, arrow proof of z. And this type, a priori, is not in the image of the proof morphism. It's not the type of the proofs of some proposition. But using the rewrite rules, we can decide to make it so. That is, we can use this external quantification over propositions to define the conjunction in this way. We first define a symbol, a variable, a constant, and of type prop, arrow prop, arrow prop. And then we use this rewrite rule, saying that the proofs of x and y are exactly the elements of this type, pi z in prop, and so on. And you see that although this type a priori was not the type of the proofs of something, because we added this rewrite rule, we made it the type of proofs of something. So we don't need to add a quantifier in the theory to quantify over propositions, because we can already quantify over propositions outside. And we can do exactly the same thing for truth, falsehood, negation, disjunction, and the existential quantifier. And you see here that the proposition x and y does not reduce to anything. The proposition x and y is a normal form. It's only when we apply the constant proof to this proposition that we get the type of the proofs of x and y, and that this type rewrites to something else. It's not the proposition, it's the type of its proof that reduces. So now we are done with constructive predicate logic, and let's turn to ecumenical predicate logic. So first, before I try to explain how ecumenical predicate logic can be expressed in deductive, let me remind you what ecumenical predicate logic is, and more importantly, where it comes from. In fact, it comes from a very old philosophical question, which is, how do we know that this deduction rule holds? How do we know that from A we can deduce A or B? And this is, you have recognized, the introduction rule, the first introduction rule of the disjunction. And there are several answers that can be given to this question. And the first one is that this deduction rule holds in nature. So in nature, each time we realize, or each time we notice, or we judge that A is true, then we can also notice that A or B is true, and it is a matter of fact. But of course, it's very difficult to be convinced by this answer, because we would be very surprised if some physicists came and told us that they have found a situation where A is true, but A or B is not. And we would think that this is not possible. So if it's not possible, then this rule is necessary and it cannot be a law of nature. Another explanation is that our brain is wired in this way, so that when we have deduced A, then there is a chemical process in the brain that permits us to deduce A or B. But also this explanation is not very convincing because, for instance, computers are wired in a very different way than us. Still, they can use the deduction rule. So the deduction rule seems to have nothing to do with our brain or our mind or whatever. So a third answer was given, which was much more convincing. It is that the deduction rule, in fact, defines the meaning of the symbol or. And you can see that here you have the same idea that was already developed by Poincaré and Hilbert about geometry, that the axiom of geometry, in fact, define the meaning of the symbols that are involved in the language of geometry. But if we take this explanation seriously, then we reach the conclusion that constructive and classical rules define different meanings for the conjunction, the disjunction, the implication, and the logical constant. So these meanings are different. So these rules speak of different notions. So it doesn't mean anything to fight for or against the excluded below. It's like fighting about the statement, disjunction is exclusive. Of course, it depends what you call disjunction. If you call exclusive disjunction, disjunction is indeed exclusive. But if you call inclusive disjunction, then the statement disjunction is exclusive is false because disjunction is inclusive. You have defined it in this way. So if you follow this idea, you see that you can have different symbols like the constructive disjunction and the classical one. So for the constructive disjunction, we just use the usual symbol for disjunction. And when the disjunction is classical, we add a subscript C to it. And these two symbols, they can coexist in the same language because they are just symbols expressing different things, different meanings. They have different meanings. And it's exactly like in the same language, you can have the inclusive and the exclusive disjunction, and you don't have to make a choice between these two symbols. So what is usually called ecumenical predicate logic is a predicate logic where you have both constructive and a classical disjunction, both a constructive and a classical implication, and so on. But the question we now have to address is how can we define these classical connectives in deductive once we have the constructive ones. And one idea is to use a negative translation as a definition. So if you remember, Gödel, Gensen, and Kolmogorov, again, had defined several translations that to a proposition A that map proposition A to their translation, which is written with A with 2 bars. And the goal of this translation is that the proposition A has a classical proof if and only if its translation has a constructive proof. And if you follow a Kolmogorov translation, for instance, you have to take your formula. Here I took the formula, the proposition P and Q implies P. And to translate it, you have to stuff it with double negations everywhere. So you have to prefix every sub-formula of this formula with a double negation. So you get the formula which is in the middle of the slide, and you see that we have added 5 times double negation, first in front of atoms, P, Q, and P, then in front of the conjunction, P and Q, and then at the root of the formula, so in front of the implication. And when we see this translation, it's very tempting to think that we could use it as a definition. So it means that we should find a formulae or for A implies B, where by A implies B we mean the classical implication, A and B, where we mean the classical conjunction, so that if we apply the classical conjunction to A and B, and then the classical implication to this formula and P, So we get this formula P and classical Q implies classical P. Then if this proposition, if we succeed in making this proposition being the same as the Kolmogorov translation of P and Q implies P, then we see that this proposition will have a constructive proof, will have a proof if and only if the proposition P and Q implies P has a classical proof. And our intuition is that the classical conjunction should be like the constructive one, plus some double negation somewhere. But then the devil is in the details, and there are three possibilities when deciding where to put the double negation. The first idea was Pravitz's idea to put the double negation in front of the proposition. So you define A and classical B as not A and B, where the second conjunction is the constructive one. Then Olivier Herman and Lisa Alali had a different idea. It was to put the double negation on the propositions A and B instead of at the root of the formula A and B. So their definition was that A and B classical was not A and not B. Then I wanted to have the best of both worlds, and I decided that I could put as many negations as I wanted. So I translated, I defined the classical conjunction in such a way that A and classical B was not A and not B. But then if you look at these three possible definitions of the classical, connective, and quantifiers, you see that our proposition P and classical Q implies classical P is, in the first case, this proposition, not P and Q implies P. In the second one, it is this one, and in the third one, it is the one I have written. And none of them is exactly the double translation of P and Q implies P. You see that in the first one, some double negation in front of atoms are missing. And look at Pravitz's definition. You don't see how who would put double negation in front of atoms. Of course, you have the double negation in front of atoms in the case of Herman and Alali, but then what is missing is the double negation at the root of the formula. And in the third case, you have 4 negations instead of 2, which is not a big deal, but if you take just an atomic proposition, you don't get the double negation in front of it. So none of this solution works, and several ways to fix these issues have been proposed. So Pravitz himself has proposed to introduce not only a classical version of the connectors and quantifiers, but also a classical version of the predicate symbols. And in this case, the classical version of the predicate symbol, the zero array, the null array predicate symbol P would be not P. And using the classical predicate symbol, what you get is exactly the double negation in front of atoms that were missing. And then Frédéric Gilbert understood that changing just a little bit the syntax of propositions allowed to do the same thing without introducing a classical duplicate of the predicate symbol. So he defined the syntax of predicate logic in this way. You first have terms as usual, but then before you define proposition, you define another syntactic category, which is the syntactic category of atoms. And an atom is just a predicate symbol applied to a sequence of terms. And then you can define propositions. It's a third line of the definition, A here. And a proposition is either an atom or a conjunction or an implication or a disjunction and so on. But the embedding of atoms into propositions is explicit. So you have this symbol, the triangle, which is called the Gilbert operator, which embed an atom as a proposition. And then the trick is that this Gilbert operator comes into flavor. So even if the atom is only in one flavor, when you put this embedding in front of it, you can either use the constructive or the classical Gilbert operator. And of course, the classical Gilbert operator is just the double negation of the constructive one. So in this case, the proposition P and Q implies P now is written in this way because you have to make the embedding, the cast of the atom into a proposition explicit, and you have to choose a classical cast. And using the definitions we got, you get that this proposition is exactly what you wanted. So you have double negations everywhere. And Émilie Greenenberger did the same thing for the choice of Herbrand and Allali. And of course, the situation is a little bit different. So she defines the terms exactly as usual. But then she defines a notion of pre-proposition, which is a little bit like the intermediate syntactic category of the second case. But here you have everything that you called propositions before. And then you have to promote, to embed these pre-propositions into propositions by a kind of dual of the Gilbert operator. And if you do so, of course, you have also a constructive and a classical version of this symbol. So now the proposition P and Q implies P, where everything is classical, is written as it is on the last line. And when you unfold the definitions, you get exactly what you wanted. Now let's go back to deductive and how can we and ask ourselves how we can embed ecumenical logic in deductive. So you remember that we had two things in deductive. We had proposition P and then the type of its proofs, proof of P. And what we have decided to do is to incorporate the first to choose the solution 2. So the solution 2, remember, is the one where here on line 2, I'm waiting for the slide to come, where you don't put the double negation at the root of the proposition. You only put it on the subformulae. And to fix the problem, you have to put this dual Gilbert operator in front of it. And its classical version is the double negation of the constructive one. And we have decided to incorporate this dual Gilbert operator in the symbol proof. So we have two symbols, the usual constructive symbol proof that maps a proposition to the types of its proofs. And we have another one, which is proof classical, proof C, which is a proof of not of its argument. And then we can just define this symbol and the classical operators. So to define this symbol, it is like the proof symbol function mapping proposition to types. And you see that you have a rewrite rule expressing that if you have this symbol, the classical version of this symbol applied to X, then this reduces to the constructive version of this symbol applied to not X. And this is this reduction rule that puts the double negation in front of the proposition. Then for all the other double negation, they are brought by the connectives and quantifiers themselves. And you see, you recognize here in the second group of declaration under rule, we have declared the classical implication, which is of type prop, arrow prop, arrow prop. And we have a rewrite rule expressing that X implies Y classical, rewrites to not X implies not Y. And you see that there is no there is no double negation in front of the proposition because we are using the solution 2. And you can do the same thing for the conjunction and for the disjunction and so on. And you get an embedding of ecumenical predicate logic in deductive. So we have both constructive and classical symbols. And when you have a formula which is purely classical, that is all the symbols, including all the connectives and quantifier and the proof symbol. So when you have a classical type, then this type is inhabited if and only if the corresponding proposition has a classical proof. And if you have a purely constructive proposition, so a proposition using only the constructive connectors and connectives and quantifiers and the constructive proof symbol, then this type is inhabited if and only if the proposition, the corresponding proposition, has a constructive proof. So I still have 4 minutes to tell you about more theories that we have been able to express in deductive. And of course, predicate logic was just an example. So I showed you how we went from minimal predicate logic to constructive predicate logic and then to ecumenical predicate logic. But it's just one example. It's a very paradigmatic example, but it's just one example. And here are some other theories that we have been able to express. And you have all these bright people here. I will not mention all their names, but you should read them. So first, of course, any theory which can be expressed in predicate logic can be expressed in deductive. Even if you have axiom schemes, I have showed you just a little bit how we could use the external quantifier to define axiom schemes. We have been able to express a simple type theory. We have been able to express all pure type systems, including the calculus of constructions. We can express inductive types. And more recently, we have been able to express universes, predicate subtyping, and this opens the way to have proofs coming from PVS in deductive. PVS is a proof system that implements an extension of simple type theory with predicate subtyping. We have been able to express proof irrelevance, which is a feature of some type theories. And universe polymorphism is almost finished. Gaspard Ferret and Guillaume Genestier will defend their thesis soon. Let me show you how you define simple type theory in deductive and how we define the calculus of constructions. So you're not supposed to read everything, but you are supposed to notice that it is almost the same thing. And it is also almost the same thing as predicate logic. So you recognize the old friends here, the symbol proof, the symbol prop, the implication, the for all quantifier. But you see that in a simple type theory, you have more things. Basically, you have the 4 last lines where you define a type omicron for propositional contents and arrow type to build functional types that you have in simple type theory in higher order logic, while you don't have them in predicate logic. And you see that the case of the calculus of construction is almost the same thing as simple type theory with very few differences. So the differences are that the symbol arrow is replaced by a dependent version of the symbol arrow. The implication is replaced by a dependent symbol for implication. And then you have an extra symbol pi. I will not discuss today. We could spend a full hour discussing about the use of this symbol. So there are very few differences and with minimal predicate logic as well. And they are very easy to explain because simple type theory is basically minimal predicate logic with propositional contents and functionality. And each of these features is expressed just by 2 lines, 1 declaration and 1 rewrite rule. And again, we can be more ecumenical again, because instead of saying you have to make a choice to have either the dependent arrow or the non-dependent one, you can take both. And if you want to use an arrow that is dependent, you use the symbol arrow D. And if you have arrow which is not dependent, you can use the arrow symbol. And when you have a proof that is expressed in some fragment of this very big theory, then you know that the proposition you have proved is provable in the small theory that you have considered. And this is the basis of the way we do reverse mathematics in deductive. So for instance, it's easy to see that all proofs that are expressed in simple type theory can be translated to the calculus of constructions. And in simple type theory, you have a non-dependent arrow that you can very easily replace by a dependent arrow that happens not to be dependent. And the same for the implication. And then as you don't use the extra symbol pi, it's not harmful that this symbol pi exists, but you just don't use it. But in the other direction, it works sometimes, but not always. So if you have a proof in the calculus of construction that uses genuinely the features of the calculus of construction, you cannot translate it to simple type theory. But if all your arrows happen not to be dependent, and if the symbol pi is not used, then of course, you can transform your proof so that it is expressed in the fragment corresponding to simple type theory. And when François Thiré started his PhD 4 years ago, I asked him to look in the arithmetic library of Matita. So Matita is an implementation of the calculus of constructions, which part of it we could translate to a simple type theory. And in fact, it happened that almost all the library could be expressed in simple type theory. So the very specific features of the calculus of construction were not used in these proofs. In fact, we have the first ever proof of Fermat's little theorem in constructive simple type theory. So why is it the case? Because we had before several proofs of Fermat's theorem. First, Fermat's own proof, but it was not a formal proof, so we don't care much about it. Then we had classical proofs in HOL Light or in PVS, for instance. But we didn't know if these proofs were constructive or not. And in both systems, you cannot ask the question, is the proof constructive or not? Because the logic is classical by construction. We had a proof in Matita, as I told you, but this proof in Matita, we didn't know if it was expressible in simple type theory. It's not a question you can ask in Matita, because in Matita, you have dependent types and so on, and you cannot ask not to use them. So we got the first formal proof of Fermat's theorem in a very weak theory, which is constructive simple type theory. This is the main result of François Thiré's dissertation. So he started on the left of this picture with a Matita proof of Fermat's little theorem. I'm speaking of Fermat's little theorem, and not Fermat's last theorem, of course. It's a simple theorem of arithmetic that Fermat indeed succeeded proving. Then he has translated this proof in deducti in the theory of Matita expressed in deducti. So this is the blue arrow. Then there is this partial function from the theory of Matita expressed in deducti into simple type theory expressed in deducti. But in the case of the proof of Fermat's last theorem, all the proof could be translated to simple type theory. And then he has been able to express this proof, to export this proof to HOL Light, to Isabelle HOL, to Koch, to Lin, to Matita, and to PVS. In fact, to PVS, we did it with César Munoz from the HOL Light proof. We adapted the translation from a simple type theory to HOL Light to the case of PVS. Okay, so I told you at the beginning I would speak about Wikipedia for formal proofs, and so far I haven't. So we are reaching the end of the talk, so maybe it's a good time to speak about it. You see that we have all these proofs, such as starting with the arithmetic library of Matita that can be formulated in many different systems. And we thought it was a good idea to have an online repository where users of various systems could find these proofs. And you can visit the website. The URL of the website is logipedia.science. So these proofs, they are expressed all in deducti, but of course deducti is just a logical framework. It's not a theory per se. So they are expressed in various theories in deducti. But in fact, it's not, what really matters is not the theory. It is the symbols and rules that are used in the proofs. And if the symbols and rules fit within a fragment of the theory, then you can export them to a genuine proof in this theory, in particular to an external theorem prover. So I'm reaching my conclusion. And one conclusion is why does it work so well? As I told you at the beginning of François' PhD, I was kind of skeptical that we could translate a lot of proofs from Matita to simple type theory, and it happened that the whole library, arithmetic library of Matita could be translated. And in fact, the reason why it works, it's because the proof systems we develop, they implement very explicit theories. We develop proof systems that implement more and more advanced theories with inaccessible cardinals and quantification over the inaccessible cardinals and so on. But in fact, in the genuine proofs, we only use a part of it, a very tiny part of it. And this is why our proofs are much weaker than the logics we implement. They can be expressed in much weaker theories than the theories we implement. And we had previously two empirical evidences of this. It is that the proof systems we developed, they implement very different theories, but the libraries are very similar. So whether you have the axiom of choice or not, whether you have a universe polymorphism or not, whether you have the excluded middle or not, eventually you prove that 0 plus x is equal to x, and that may be more difficult theorems. But the theorem that the sum of the derivative of the sum of two functions is a sum of the derivative, you can prove it everywhere, and whatever whatever system you are using. And there was another early empirical evidence is that since logic has been existing, mathematicians do not seem to care much about the axiom they use in their proofs. They can develop a proof in set theory, then one day you want them to express this proof in type theory, it seems to work, and they are not really interested in the axiom. Some mathematicians don't even know the list of the axioms of set theory. So they think they use set theory, but in fact they don't even know the axioms. And mathematics works in this way. It works in this way. So it means that the axioms do not matter as much as we think they do. And to conclude, this is my real conclusion now. Some of you may have heard about the Qed Manifesto and the Qed project that was at the end of the 20th century. In 1993, Bob Boyer and some of his colleagues had the first idea to build something like Logipedia. And at that time, it didn't go very far. So many people are still skeptical we can do something with Logipedia. But of course, skepticism is something good. So I don't want to convince them. We just need to do the things. But there are three main differences between the situation we have now and the situation we had at that time. First, we understand much better the theories that are implemented in the various proof systems, and we understand their relations much better. Then we have new logical frameworks to express these theories. And in 1993, we didn't have tools to describe these theories, or very few. And now we have understood that we should not try to translate all proofs from one system to another. But first, we have to share the proofs. And then whenever using reverse mathematical techniques or analyzing the proofs, we understand that they don't use some of the advanced feature of the logic in which they have been developed, in the theory of advanced feature of the theory in which they have been developed, then we know that we can translate them, but we should not attempt to translate them all, because of course there are very few, but some theorems that can be expressed in one formalism and not in others. Thank you very much.
Thank you very much, Gilles. So now I have some time for questions, comments, or any other kind of interactions. So I would like just ask you to manifestate first in the chat if you have some question or comments to make some kind of line and avoid everybody talking at the same time. While we wait for questions, Gilles, if you want, you may turn off the presentation so people can see you now.
Yeah, sure. Let me see if I remember how to do it.
Yes, it would be great, yeah.
Hi, Gilles. Can I ask a question?
Yes.
It's more or less on where are you now in the project? I mean, what are you doing right now?
Okay, so it's a good question. We have expressed many theories in deductive, and we have evidence that we can translate proofs to deductive. So we have done that with a large part of the library of Matita. This was the work of Ali Asaf. Then we have done this with HOL Light as well. We have done that with a smaller system, which is called Focalize. More recently, we have done that with Agda. And we have part of the COC library. In particular, there is a formalization of the Euclid's element in COC, which is called GeoCoq, which has been developed by Pierre Boutry. And then Pierre himself and Gaspard Ferret have translated this library to Deducti. So we now have some experience to import proofs that have been developed in external provers to Deducti. The next step is the transformation of the theories in which these proofs are expressed. And here we don't have much done yet. The only example big example we have is this arithmetic library of Matita, which is 300 lemmas. And then we have the next step, which is to have exports to different theories. And when we have a proof in simple type theory, we can export it to HOL Light, Isabelle HOL, Coq, Matita, and PVS. But the library itself is still very small because there are these 300 lemmas. And the populating this library is a project that we are planning to do in the next 4 years. And to do so, we are trying to build a consortium at the European level so that we have more people involved in the project. So we can say that we are still at the level of a proof of concept today, especially for this translation phase. The importing proofs from an external system to Deducti and exporting proofs from Deducti, we are more mature, but for the proof transformation, it's still a proof of concept. And finally, there is one reason why we got really interested in proofs in first-order predicate logic is because there are several projects to define a common language to express proofs built by automated theorem provers, not interactive ones, but say SMT solver, set solver, resolution provers, and so on. And here, of course, as you have seen, we know how to express them, and we are trying to see if Deducti and Logipedia is relevant for this kind of proofs.
Gilles, I remember I have talked to you before about that some groups are using machine learning techniques for identifying equivalence proofs. Are you on plan to use some kind of technique like this or no?
So far not yet, but there are several people interested in this. So with different approaches. So I cannot give you a very synthetic view of this, but let me just mention a few projects. One question is when you have a proof and you want to export it, you want to translate it to another language. From time to time, you cannot have a full proof, and you have a proof with holes in it, and then you have to use an automated theorem prover to fill the gaps. It's in particular the case where you use a very fast automated theorem proving tool. So the people who develop this tool, they don't want to instrument their code too much because it slows the system a lot. So they don't really give you a proof. They give you a kind of proof trace, and you have to rebuild the proof from this partial information. And it is also the case with systems like PVS, where it's very difficult to have a formal proof, but it's relatively easy to have a sequence of lemmas, and then you have to fill the gaps between the lemmas yourself. And there is a project to use artificial intelligence techniques such as machine learning and also abduction if you fail when filling the gap, the artificial intelligence system should help you to find a relevant lemma that maybe you have forgotten to take with you in the proof. So this is one direction. Another direction is that the people who really want to use big data to train machine learning algorithms, they are kind of interested in having very big databases, and databases that are not specific to one prover. And so this is another project with different people. So I don't know exactly how these different projects will converge eventually, because they are all of them very premature. So it's difficult to see exactly where we are going. But I'm sure that more machine learning in automated theorem provers, and also in interfacing proofs coming from different places, is a technique that will prove to be useful.
Thank you very much. Any other questions or comments?
There was one.
Oh, sorry, there is one. There are Luis Carlos.
Are you listening?
Yes.
Are you listening?
Yes, I can hear you. Yeah, I am.
I think it's frozen. Gilles. In the slide that you present, when you start talking about translation, is a slide that you had a question mark related to translation and definition. And you know, I'm sure you know that one of the ecumenical approach receives always paper. I don't know. That's not like ecumenical. I mean, get translation that you can show that it is really good. That takes in proofs, right?
Luis, Luis, yeah, your audio is not okay. Luis Carlos?
My audio is not okay?
Yes.
It's not for me.
Gilles,
are you listening?
I didn't hear anything. I'm sorry.
Can you write, please?
So,
okay. So
everyone, or
no, so,
did nobody?
Okay. Also, move to.
Luis Carlos is typing. So while Luis Carlos is typing, to avoid losing some time, Alexandre?
Move to the next question.
Okay, no, Luis Carlos, now we can hear you. You can talk now, Luis Carlos.
Can you hear me?
Yes.
Can you hear me?
Yes.
Okay. Okay. My question was that when you showed the slide about the good against in translation, there was a question mark relating translation and definition, right? And the usual criticism to the ecumenical approach is that you don't need it. You can introduce the class of operators. So there's nothing new in the ecumenical approach. But there are some answers to these criticism. For example, Peter Krause says that the ecumenical approach is not the good against in translation. He can show that it is against in translation. This is one thing. The other thing is that the spirit or the ecumenical perspective takes into consideration proofs. You're not just translating a language from one language to the other. I mean, the use of ecumenical operators is really related to proofs, how operators are used in the proofs, right? So you do not translate anything. So that's why you can have hybrid expressions. Now, you can have hybrid axioms with parts of the axioms classical, some parts of the axioms constructive. And it's very interesting in that sense. So what is your opinion about this idea that we don't need ecumenical? We just translate, define them by means of translation? This is the first question. And the second question.
Okay.
Can I make the second question right now?
I'm listening.
Yeah, no, it is related. It is related to the definition that you showed of conjunction in terms of product and the condition and implication, right? That is, as you're completely right, it goes back to Russell. Now it is called Russell-Profits translation, Russell-Profits modality. It doesn't matter, but it really has some resemblance to what has been done in that variation of the F system of the atomic polymorphism, where you restrict the instantiation of the product to atomic instantiation. I don't think that you have this restriction in your system, right? The restriction to atomic instantiations of the product. If you have the restriction to atomic instantiation, you need a more general result that it's called instantiation overflow, that shows how to, reduce, to obtain the elimination rules for conjunction, etc., etc., etc. If you have the restriction to atomic instantiation, you need some extra reductions, some extra proof transformations. So I'm curious to see how the definitions really work in terms of proof transformation, etc., etc. Thank you for the talk again. Great talk.
Thank you. So I missed the last part of the question, but I think I understood the question, so I could reconstruct what you were saying.
Okay.
If I'm wrong, please correct me. So first, I put this question mark because I'm skeptical that the negative translation can be used as a definition. And as we saw, each of the possible definition has some flaws, and we have ways to fix them. But we have to introduce either this Gilbert operator, or to introduce a negative variant of each predicate symbol, or to introduce a symbol in front. So the idea that I had at the beginning that we could just use a negative translation as a definition obviously was too naive. Then I have to mention that relating in this way constructive and classical connectives is just one way to do ecumenical logic. There are many other ways, and in particular, Émilie Grenenberger, who I mentioned already, who is starting a PhD currently. She has given purely a declarative version of ecumenical logic, where you have deduction rules for classical connectors, and you have other deduction rules for constructive ones. And she has proved that the two fragments, purely constructive and purely classical, were correct and complete with respect to, say, NJ and NK. So we don't have to use the negative translation. It's just, let's say, an implementation method to implement negative ecumenical logic, but we could decide to implement it other ways. And finally, I think the main interest is to have this so-called hybrid formulae. And in particular, of course, if we only take the constraints that purely constructive propositions should be provable in ecumenical logic if and only if they are provable in constructive predicate logic, and the same for the classical for the classical fragment, then these constraints do not tell us anything about the mixed formulae. So it could be very well that my favorite mixed formula, which is, as you know, P and Q implies P, where the conjunction is classical, but the implication is constructive. It may be very well the case that this formula is provable in some ecumenical logics, but not in others, because we have a degree of freedom, which is which mixed formula are provable or not. But it seems that in all ecumenical logics we have so far, this proposition is not probable. And it seems to mean that there are some determinacies that make us go in a direction where this formula is always not probable. So maybe there are good reasons why it should not be probable. So yeah, I completely agree with you to sum up that ecumenical logic does not boil down to negative translation. Then on your second question, the quantification we have on propositions outside the theory, so in the logical framework itself, is not restricted to atomic propositions. So this is why we don't need to prove by induction on the structure of the formula, for instance, that we have the elimination rules or the introduction rules for the conjunction for complex formulae, because we get it very directly. So of course, this could be a work.
You can just instantiate,
Yeah, you can just instantiate. So of course, it makes a system impredicative. So if you want to remain predicative, this solution doesn't work, and we have to find another solution. What is interesting is that the quantification per se is predicative, but adding the rewrite rule it's in fact the rewrite rule which is impredicative and not the quantification. And this is very strange, because when you quantify over a proposition, you don't get another proposition, you get a type. So you can say that you quantify over propositions to bit types, which is fine, which is predicative. But then when you add the rewrite rule that the type of the proofs of the conjunction rewrites to this other type, then in fact you implicitly define the conjunction as a reverse translation of this type. So you understand a posteriori that your quantification over a proposition was able to yield a proposition, while at the beginning it was a type. So there is I'm not completely sure I understand where impredicativity is hidden, but I'm pretty sure it is hidden somewhere.
Very interesting. Thank you, Gilles. Thank you for the talk.
João Marcos?
Gilles. Bruno.
Yes.
Can you hear me? Hi.
Yes, I can.
Gilles, so thank you very much for the talk. Excellent. As you recall, you were an invited speaker at the workshop Theory Improving Components for Educational Software that I was organizing, and that did not happen this week in near you. So I am near me, it's so far away, but I'm under the impression that you might not have given such a different talk to us there this week, that you would be talking also about Logipedia. Is that true?
Yeah, this is what I was planning to do.
It is. Just compliment. I would like you just to say something about how you would connect this to educational interests. I know that you are a textbook author, that you're very much interested in education. Could you say something about how Logipedia would connect to that?
Okay, so it's a kind of long-term project, but we noticed that in the Logipedia community, the people who wanted to contribute to Logipedia, there were a lot of people who were also using formal systems to teach, but not to teach formal systems. Many people do that, but to teach math to undergrad students, or to teach math even to high school students. High school students are not very convinced, but I think it's worth trying. And their idea is that we have to maybe not to put lambda calculus at the beginning of high school, but that we have to give a more formal account on the mathematics we are teaching. And in particular, to put back the notion of proof at the center of the mathematical teaching, so that the student should not just learn notions or methods or algorithms, but also to learn how to do a proof. And then there was one question was how can Logipedia help in doing so? So I don't think the high school student will interact with Logipedia directly, but we could, for instance, imagine to write a textbook where all the statements of the theorems are formal, and we know that they are formally checked even if we don't give the formal proof. This way we could, for instance, have a very clear view on which lemma depends on which. And we could also have a very clear view on the corner cases. So as you know, for instance, a theorem like the bisector of a triangle meet in one point is false if you consider that a flat triangle is a triangle. So either you have to give a definition of triangle that excludes flat triangles, or you have to add a hypothesis to your theorem that it applies to non-flat triangles. Or you have to give a different formulation of the theorem, for instance, that if two of the bisectors meet, then the third one also goes through the intersection point. So you have many ways to make the statements of the theorem more precise, more formal, to understand which definitions are used in which proof and which lemmas are used in which proof. And I think this can be of some benefit to math teaching, at least in the first year of university, and maybe in high school. But we have to try. We have to try that. Of course, this is wishful thinking, because as long as we have not written this textbook and showed that it works in practice, we cannot claim anything. But I think it's worth trying.
Yes. Thank you very much.
César Muñoz?
Yes. Hi, Gilles. Hi, everyone.
Hello.
Great talk, Gilles. Can you hear me?
Yes, of course.
Oh, okay. So I have a quick question. I know that it's almost midnight for you. Translating proof is really nice, and I was amazed that you and your group were able to translate a proof that is not completely trivial, the Fermat-Little's theorem, into different systems with different logics. I mean, constructive logic and even a logic like PVS. I mean, that is amazing. However, I mean, if you look at in Logipedia, the proof of the three systems, and then you look at the Matita proof and the Matita statement, you understand what you're talking about. Then you look at the translation in deductive, and then you can, I mean, it's a little bit more complicated, but you can still read the statement and the proof. If you look at the PVS, and I'm a PVS expert user, I have absolutely no idea what the statement is that statement is the statement of that proof. So in particular for sharing libraries, one of the issues is that libraries are live objects, are objects that you have to maintain, that you have to add, and maintaining and adapting and even using a library that is translated from a different system. I think that this is a big issue for a project like that. What do you think?
Okay, so as you know, I don't have a real answer to this question, but I have some elements. One of them is that we have to keep the statement readable, but maybe not the proofs. And I will make a comparison with what you do when you write a program. Then you compile your program to assembly code, and very few people try to edit the assembly code and to optimize it. So if you want to modify the program, you have to modify the source code and then to compile it again. So I guess it's a little bit the same. If you have a proof which has been developed in PVS, then you can share it with other people. But these people are not going to read the proof. It would be like reading assembly code. And if ever they want to modify the proof, they have to go back to the PVS code and to recompile the proof, to modify the PVS code and to recompile the proof and to use it again. So maybe they don't know how to use PVS, and then they will have to find someone to do it for them. Exactly as if you use a library which has been developed in Fortran and you use it in Python, then you cannot modify the library unless you learn Fortran yourself, and less and less people know how to maintain this library. But already making the statements readable is a lot of work. And when we export proofs, for instance, the proofs of Fermat's little theorem, we see that it comes with all its definitions. So it has its own definition of natural numbers. It has its own definition of addition. It has its own definition of multiplication, of factorial, and so on. And of course, we don't want to have a definition of addition which is specific to that proof. So one thing we have to do is to understand how we can connect this addition that comes from Logipedia to the native addition of PVS. Or maybe one day we will have only proofs in shared databases. Probably it would not be Logipedia anymore at that time. It will be in the 22nd century. And we won't have any local proofs, any local libraries. So if we look, for instance, how we use Wikipedia, we are not keeping a local copy of our knowledge that we interface from time to time with Wikipedia. We always go with the external Wikipedia, which is outside our computer. And maybe one day we are going to do the same thing for proofs, but this day, I'm not sure we will live long enough to see this. But maybe it's something we should investigate already, how we can put all our proofs there so that there is just one addition that has been defined for the whole library Logipedia, and then in PVS or in HOL Light or in Qed, you have just the copy of this definition. So it's a very long perspective, but you're right, it's a very, very important problem, and it's probably the next research problem we'll have to solve.
Thank you, Gilles. So, I apologize, I got disconnected immediately after I asked the question, but we can talk about that later. Sorry about that.
Yeah, in fact, it's almost an answer I already gave you to this question. So, so you know,
okay.
what
I'm
going to say.
Sorry about that. Thank you.
The talk will be available online in a few minutes after we finish here, so you can watch it.
Thank you.
We have another question from, I'm really sorry, I will probably mispronounce, Guiano, I'm not sure. Would you like to talk?
There's a question, what is RA with 2 bars?
No. This was when you transform a proof so that it squeezes in a smaller theory, do you get a longer proof?
Okay, yes, of course. So there is an expansion factor which is between 5 and 10. So our goal is to maintain this expansion factor big but constant. So as we translate the proofs step by step, lemma by lemma, this expansion factor is constant, but it's big because the proofs in deductive, we try to make them very explicit. So we are interfaced with languages where, for instance, you have implicit arguments or many ways to make the proof shorter, more implicit. But we don't want to do that because then when we export these proofs to other systems, we have to reconstruct some information. So we try to have the information as explicit as we can. And I have to say that at some points we failed of keeping this translation factor constant. And I will give you one example. At the very beginning, the first translation we had to Deducti was a translation of HOL Light, and it had been written by Ali Assaf. So Ali Assaf told me that in a HOL Light they had some sharing, and I told him, well, you shouldn't care about sharing. We have a very fast computer, so even if you lose the sharing, we will be able to type check the proof, to proof check the development. But it was completely wrong. So Ali had to rebuild the sharing in Deducti. Otherwise, the proof, it's just impossible to check it. So we have to be very careful about efficiency. And when I'm speaking of efficiency, I'm speaking of the size of proofs. So if we lose sharing, for instance, we lose a lot.
Sorry, I always do this. I was talking with the microphone muted. Any other question or comment? So I'm just to stop the recording.